So you know that, so whenever the water is flowing over a spillway, it acquires a very high velocity, because when the water is stored on the upstream side, so it has got a huge potential energy. So whenever the flood occurs, it flows over the spillway. So that means the potential energy gets converted into kinetic energy as it flows down. If the water with very high velocity is discharged into the riverbed, then it starts covering the riverbed. So if this covering is not checked, then the cover will extend backwards and try to endanger the spillway as well as the dam. So as such, to protect the river bed against this cover, the higher kinetic energy of water should be dissipated before it is discharged into the river channel. So here, for dissipating the kinetic energy, we are following two methods. That is, we have to develop an hydraulic jump at the toe of the spillway, or we can use different types of energy dissipators such as stilling basins and the bucket. So you know that you have studied in your fourth semester chapter that hydraulic jump. So hydraulic jump is nothing but a sudden and turbulent passage of water when the water moving with a supercritical velocity changes to subcritical state. So that means the flow in the hydraulic, that is a sudden rise in the water level when the flow comes from supercritical state to a subcritical state. So then this sudden rise in water level is known as hydraulic jump. So this generally occurs at the toe of the spillway. So here the flow in a hydraulic jump is accompanied by the formation of turbulent rollers, and there is a considerable dissipation of energies. As such, the hydraulic jump is the most suitable and effective means of energy dissipations. So depending upon the initial Froude's number, we have different types of jump. So when you know that when Froude's number is equal to 1, so then the flow is critical, hence no jump can form. So if the Froude's number of incoming flow is greater than 1, so then only hydraulic jump forms. So that means when Froude's number is between 1 and 1.7, so it is less than 1.7, then water surface shows some undulations and is known as the angular jump. So when such type of jump forms, the energy dissipation is around 5%. If the Froude's number is greater than 1.7 and less than 2.5, then series of rollers are developed on the surface of the jump, and which is known as a weak jump, and the energy dissipation is around 20%. But when the initial Froude's number is more than 2.5 and less than 4.5, so the entering jet of water will oscillate back and forth from the bottom to the top, and this continues, and this type of jump is known as an oscillating jump, because the jet oscillates from the bottom to the top and again goes back to the bottom. So in that way it dissipates the energy, and this type of jump is known as an oscillating jump. So energy dissipation may go as high as 20 to 45%. When the Froude's number is greater than 4.5 and less than 9, a well-balanced and a stable jump is formed, which is known as a steady jump. So energy dissipation will be more than 45% and may go up to 70%. But when Froude's number is greater than 9, okay, so the jump action is very rough with a strong surface waves that are formed downstream of the jump, and this is known as a strong jump, but the energy dissipation may go as high as around 85%. So we also, the other type of energy dissipation is by using a stilling basin, okay, at the downstream of the, or at the toe of the spillway. A stilling basin is nothing but a structure in which a hydraulic jump used for energy dissipation is contained within it. Either it is partly or entirely contained within the basin. So here certain accessories are provided, such as chute blocks or baffle blocks or end sills, okay, to reduce the length of the jump. If you reduce the length of the jump, since the jump is contained within the stilling basin, so that will reduce the length of the stilling basin as well as the cost of the stilling basin. So these accessories like chute blocks or baffle blocks or end sills will definitely improve the dissipation action of the basin and thus stabilize the jump. So we are providing stilling basins for various different types of stilling basins. For example, like when the force number is between 1.7 to 2.5. So that means when the force number is less than 2.5. So for this case, a simple horizontal apron can be provided at the toe of the spillway. So as the flow doesn't have much turbulence here, so no accessories like chute blocks or baffle blocks or end blocks are provided. However, the apron should be sufficient length to contain the jump. So you know that if y2 is the sequent depth or the final depth of the hydraulic jump, then the length of the apron, that is the concrete apron, can be provided will be equal to 5 times the final depth of the hydraulic jump. So this case of horizontal apron that is provided at the toe of the spillway will be generally for force number between 1.7 to 2. For stilling basins, for Froude's number, which is definitely greater than 2.5 but less than 4.5, we call it as a type 1 stilling basin. So here we go for a chute blocks, and also end sills can be provided. It is an optional. So generally the chute blocks are provided at a distance of 2.5 times the initial depth. The spacing between the chute blocks is 2.5 times so generally chute blocks are provided at the toe of the spillways. Its spacing is 2.5 times the initial depth of the hydraulic jump, whereas the width of the chute blocks will be equal to the initial depth. So the length of the chute blocks is minimum is 2 times the initial depth. So here the end sills which are provided at the end of the apron will be about 1.25 times the initial depth. So that way here the length of the stilling basin will be decided based on the given table, which I'll be discussing in the next slide. So the basin is provided the chute blocks and end sill is optional, as I told you. The size and space of the chute blocks are I have already told in the figure. So length L will depend upon here. So if the Froude's number is 2, so therefore the length can be 4.3 times the final depth of the hydraulic jump. If the Froude's number is 3, then it is 5.3 times the final depth of the hydraulic jump. Whereas if the Froude's number is around 4, then it is around 5.8 times the final depth. So likewise, like if the Froude's number is around 5, then it is 6 times y2. So that will decide the length of the stilling. If the Froude's number is greater than 4.5, then we go for the stilling basin depending upon the velocity of the incoming flow. If the velocity of the incoming flow is less than 15 meters, then we go for type 2 stilling basin. So here it is similar to the type 1 stilling basin, that we go for a chute blocks as at the toe of the spillways. In addition to that, we have the baffle blocks. So the dimensions of the chute blocks are given in the figure. So where the width is equal to initial depth, the clear spacing between the chute blocks is equal to initial depth of the hydraulic jump. So the baffle blocks are provided at a distance of 0.8 times the final depth of the hydraulic jump. So therefore the baffle wall the height is equal to h3, which is given in the table. So the slope is generally 1:1. So this what is h3 and all the height of the baffle blocks, whereas the height of the end sill is given in the table. So this is the arrangement that and even the length can also be decided from the table. So now you know that when the incoming velocity is less than 15 meters per second, then we go for type 2 stilling basin. This basin utilizes the baffle blocks, which the baffle blocks were not provided in the type 1 stilling basin. Then we also have an end sill. So the size, spacing and location of chute blocks chute blocks are shown in the figure, and the length L, height h3 of the baffle blocks and height h4 of the end sill can be got from this table. So it all depends upon the final depth of the job. For example, if the Froude's number is 6, then length will be 2.5 times the final depth. Similarly, like h3, we have 1.7 times the initial depth. So like this, we can get the height of the baffle blocks as well as the height of the end sills from this table. So what is the advantage of providing the baffle blocks? By providing the baffle blocks, the length of the stilling basin is considerably reduced, because the dissipation of the energy is accompanied by the hydraulic jump action as well as the striking of the jet, the incoming flow against these blocks. So that in turn it dissipates the energy. By providing a baffle blocks, these baffle blocks will be subject to very large impact forces due to the striking of the incoming. So when we have the velocity of the incoming flow here, which is exceeding 15 meter per second, then we go for type 3 stilling basin. So here also it utilizes the chute blocks as well as the end sill, but the baffle blocks are avoided because in the previous case we have seen that in type 2 stilling basins the incoming flow will always will have an impinging action on the baffle blocks, and that's the reason why we have eliminated the baffle blocks, and instead of that we have gone for a dentated sill. So okay, which has got a teeth like this. So okay, so this that was a solid end sill in the previous case. In this case it is a dentated sill. So the height of the chute blocks and the height of the this end sill is given by point, say h3 is h2 is 0.2 times final depth. So like this the dimensions are given here. So even this height of this block is equal to initial depth. Similarly the spacing is equal to the initial depth of the hydraulic jump. So length of the stilling basin will depend upon the table that the previous case. So in this case only chute blocks are provided, and instead of solid end sill a dentated sill is provided. So the baffle blocks are not provided because of the high velocity, because velocity is more than 15 meter per second. These blocks will be subjected to very large impact forces. So that's the reason why we have eliminated baffle blocks, and there is a possibility of cavitation on the downstream side due to a very large negative pressure that is developed on the downstream side. So by eliminating baffle blocks, the dissipation of energy is however accomplished by hydraulic jump action. So that's the reason why, since the baffle blocks are not there, so the length of the stilling basin is slightly greater than the type 2 stilling basin. So for which we have given for different Froude numbers, we can decide the length of the stilling basin. So for example, if Froude number is 6, then length will be 4 times y2. So the stilling basins that we discussed in the previous case, that is like type 1, type 2, type 3, they're also called other types of energy dissipators known as the bucket type energy dissipators. So these bucket type energy dissipators consist of an upturned bucket like this. So this is the spillway, and at the top of the spillway this upturned bucket is provided, so to deflect the water over the spillway. So from the spillway, so these bucket type dissipators can be used for an overflow spillway and becomes more economical than the stilling basin when Froude's number is more than 10. So we have discussed various for various Froude's number stilling basins. Similarly, when Froude's number goes as high as more than 10, we can go for a bucket type energy dissipation. So this type of energy dissipations may be used when the river bed is consisting of a very stiff rock. So there are three types of bucket type energy dissipations, like solid roller buckets, slotted roller buckets, as well as the sky jump buckets. So this is a case of a solid bucket. So whenever the flow comes from the or flows from the spillway and comes to the bucket part, so here there are series of rollers that are formed here. So one type of roller is that is moving in the anti-clockwise directions and will be contained in the bucket itself, and that is known as the bucket roller. So and the downstream of the bucket, so there are a series of rollers that are formed which are moving in a clockwise directions and known as a ground roller. So intermingling of the bucket rollers as well as the ground roller, in addition to the boils that are formed, causes the energy dissipation. So here a solid roller bucket consists of a bucket like apron with a concave circular profile, as I told you in the previous slides, which have a very large radius and a deflector dip as shown in the figure. So when water flows over the bucket, the entire sheet of the living bucket is deflected upwards and two elliptical rollers are formed, which I discussed. So one of the rollers is moving in anti-clockwise direction, okay, is developed on the surface of the bucket, and therefore it is known as a roller bucket. The other roller is moving in the clockwise direction and is developed slightly downstream of the bucket, which is known as a ground roller. So these movement of the roller, as I told you, along with intermingling of the incoming flows, causes the dissipation of the energy. So here the upward deflection of water of the by the bucket lip will create a very high boil on the water surface and a violent ground roller. So this ground roller, it tries to remove the bed materials backwards and deposits the same against the lip of the bucket. So due to the material that is trapped in the bucket will definitely damage the surface of the bucket by the abrasion action. So these drawbacks of solid roller buckets can be removed by a slotted roller bucket. So therefore we have gone for, instead of as here, so we have got a slots, which here here it consists of a bucket like apron again with a concave circular profile, but of a large radius, but has a slotted or a dentated deflector lip. The same two rollers are formed, that is that we have one moving in the anticlockwise direction known as a bucket roller, and other on the downstream we have a clockwise moving in the clockwise direction known as the ground rollers. So again the intermingling action of the surf yeah, the bucket rollers as well as the ground rollers, and with the incoming jet will cause the dissipation of the energy. So but here in this case the water leaves the bucket at a very flatter angle and only a part of it will be deflected upwards. So thus surface boil as compared to the solid roller is reduced in this case, and violent ground rollers are also there will be less violent ground rollers, which results in smoother flow on the downstream side. So in this case, the bed material, because the ground roller tries to remove the bed material and puts back to the surface of the bucket, but it will be because of this slotted bucket or deflector lip. So this material will be again thrown to the downstream side. So that means it is immediately washed out through the slots, and thus prevents the damage of the surface of the buckets. So that's the advantage of the slotted roller. We also have what is known as a sky jump bucket, which is provided at the toe of the spillway. So it is used where the tailwater depth is less than the sequential depth of the hydraulic jump, and the river bed is composed of the stiff rock. The lip of the bucket is so shaped that the entire jet of water flowing over the bucket is thrown as a free jet onto the river channel at a very safe distance from the spillway. So in this case, the energy is dissipated by the air resistance, breaking up of jet into bubbles, as well as the impact of this jet which is falling on the river bed and the tailwater. Okay, so that's how the energy dissipation takes place. So particularly this type of sky jump bucket is provided only when you have a very stiff rock here, and the water is thrown at a very safe distance. Okay, so and the tailwater depth has to be less than the the final depth. So here the dissipation of energy takes place because of the resistance of the air to the free jet. Also, whenever the jet is thrown, so it breaks up into bubbles. So that's how the energy dissipation takes place, or it hits the tailwater, or directly to the river bed or the stiff rock, and thus energy dissipation takes place. So these are the various types of energy dissipations that are provided below the spillways, and we have discussed why the energy dissipation has to take place before we leave into the river channel. By forming hydraulic jump, different types of jumps, we can dissipate the energy, and also we can provide the stilling basins, like we have US bar stilling basins or Indian standard stilling basins. Different types of stilling basins were discussed, like type 1, type 2, and type 3, and also where you can go for the bucket type energy dissipators when the Froude number is greater than 10. Okay, thank you very much.